Thank you all for joining us. Today we're going to talk about tank heating 101. This will be one of two presentations that we put together. One to highlight some of the general standard products that Chromalox has to offer, and two to go through the considerations and designing around your thermal needs, how to apply the right product and make your tank heating application work properly. You need. So my name is Derek DeBar. I am the Energy Market Sector Sales Manager and Training Manager for Chromalox. And my phone number and email is there. So if you do have some things that come up or thoughts that you want added to the second presentation, I'll be happy to cover those as we go. But for today, I'm going to cover tank heating basics, and I'm going to go through, we'll say the standard options and products available for your tank heating needs, and kind of go from there. So to begin, on a simplistic scale, tank heating. We're applying heat to a tank. You'll have a level sensor is not required, but it is certainly recommended. You have a temperature sensor. You have an over temperature sensor. Think of the sheath temperature or where the product meets the heat. And then a controller or a power switching device. It could be a thermostat. It could be a control panel. It can be a lot of things. Now this is very simplistic because frankly, this is, from the brochure, straight tank heating. These are the things to consider. However, we're going to dive into each of the products available and all the little considerations you're going to need along the way. So a standard immersion heater is one product, but there are many, and I have many examples to show you how we apply your tank as you go through. So we'll just get into it. Your electric heating options are standard immersion heaters, which are, screw plug, flanged heaters. We have what we call an LTFX, STFX, which is industry terms would be a bayonet heater. Think of removable without draining the tank. It doesn't come in direct contact. That becomes very useful in certain applications. We do circulation heaters, which can be known as indirect heating. I guess general terms would be like an inline heater if there's mechanicals on the call. Or we can use heat transfer systems, which essentially include an inline circulation heater, but also include the pump and valves and control that go along with that. So more of a system process approach. Then we have steam generators, which, if you do steam coils, steam heating, we have a full line of those, including medium voltage, which we will get into in the second presentation. We'll get into some of the more advanced design considerations. And then we got simplistic, which I got some examples to show you here in a minute of simplistic, just heating the tank, pad heaters, heat trace, and even comfort heating. You would think, why comfort heaters for tank heating? But in some applications, that works. Your heat in that type of application, you're heating the environment around the tank. So if the environment around the tank is at a maintained temperature, usually freeze protection, there's no concern of needing heat in the tank, so you're not modifying or interfacing with the tank at all. So we'll walk through them, then we'll get to the specifics. Screw plug flanged over the side kind of get lumped together as just, quote, standard industrial immersion heaters. And the terms are pretty straightforward. Screw plug heating, your most standard ones are 1 inch, 1.5 inch, 2.5 inch. We do have 3 inch available. And those are NPT screw in. We do have British standard thread flanged heaters. Usually we're utilizing the standard ANSI class flanges. We drill those out, weld in our elements, and then you have a pressure retaining ANSI flanged immersion heater. To over the side heaters, and over the side heaters are really unique. They're very cost effective way of heating a tank that's already either installed or doesn't have considerations for heating connections on the tank. So something to pay particular attention to as we go through these. As we walk through, you've got your screw plug and flanged heaters. I lump these together because they're obviously very similar. Most of the times they're utilizing metal sheath electric heating elements. So think of industrial resistors. They're welded into either the screw plug or the flange. That's simply how they bolt onto the tank. We say virtually 100% efficient because any of the heat you're generating because it is in the product or the tank is heat. It gets generated in the tank. It gets dispersed through the product, the tank and the contents of what you're heating. However, in reality, there are line losses to your connection and voltage, but that's still pushing the 96 to 98% efficiency rating on what you're generating in heat of what you're actually using in power. Quick response, you have to be a little cautious with that. Do they start heating? Do they start generating heat immediately? Yes. But the heat itself has to distribute through the magnesium oxide through the metal into the product. So it's not an instantaneous heat. Just simply it does start creating heat instantaneously. It just don't see it in the product instantaneously. Some of the cons, it becomes part of the tank. It's bolted in, it's in direct contact. So those are some considerations and designs we'll discuss in a minute on how to work around that. You've got material compatibility issues and watt densities that you don't want to scorch your product. And then you've got control. Control is part of all of this. Now you may want simplistic control of just a thermostat on off to solid state relays, which we'll discuss later in this presentation and further in the second presentation as well. So when I say screw plug heaters, if you are familiar with electric heating out there, screw plug heating, it can be, you know, brass, stainless, carbon steel, a lot of different materials for the screw plug itself. And then the element material, again, depending on the application. If it's water, it could be copper, Incolloy. If it's something more corrosive, maybe a stainless or an Inconel. And then they thread in, and you can see the prime example here on the right, where you can add multiple units to you know, beef up your thermal input. Also, there's redundancy you can build into that. But really, when the term screw plug heating comes up in any conversation or design, we're simply talking about the connection of the metal sheet elements onto the tank. So in the case of this example, this is a confectionery company. This just bolts into the tank. Now, later on, we'll talk about the Bayonet style heaters. These can be used for that. They're just not as they're maybe not the best fit always, but certainly something to consider and the control. Moving on, flange heaters. Flange heaters, again, I mentioned before that we utilize the ANSI class flanges, but that's not a deal breaker. We make square flanges, special special flanges, cut plate, whatever fits the application. But for pressure retaining vessels, most of the times it's an ANSI class flange. Not always for the pressure retention as well. It's also for fit, form, and function too. So your nozzle, it has to mount up to the nozzle. That's an industry standard. It's easy to match up. And then there's a lot of things that we'll discuss later about the type of terminal housings, the environments. Is it hazardous? Is it corrosive? How is your electrical going to be wired? What's the rating on the electrical? And that's kind of a good example here at the bottom of a general purpose terminal enclosure to a hazardous terminal enclosure to even a corrosion resistant stainless steel terminal enclosure with standoffs. So maybe the tank is at a higher temperature or higher pressure, and your wiring becomes a factor of consideration in your tank heating application. And then finally, with the direct immersion style heaters, we have the Bayonet style. And in Chromalox, we term those as our LTFX, STFX. It simply stands for large and small tanks. Basically how they fit, form, and function. Back to the Bayonet style, as illustrated on the left, these are replaceable, these are removable. So say you have a loose connection, a voltage spike, maybe had a case just recently where they didn't affix the terminal housing properly in a tank farm, got moisture down in it and had a short, so they had to replace the elements. Well, when we're talking, you know, 100,000 barrels of product or whatever size tank it is, 100 feet in diameter, and you're utilizing these type of heaters, this is a permanent structure. This isn't moving, and this is definitely something you need to consider because now they're replaceable, they're removable, and you don't have to find other means for that product in the tank to service the electric heaters. So all the benefits of the direct immersion heaters as the screw plug and the flange heaters, but in a nice removable, accessible design. And here's what they essentially look like, and that's why I was kind of alluding to the fact. In these larger tank designs, you're going to have containment walls for, you know, obviously spillage, and that goes up generally after your tanks are installed, sometimes even after they're filled. And then they can, if you're using a traditional heating element, where you need the full length of the element to remove and service the element, it's no longer accessible. In the case of the LTFX, STFX, you can see that they're open coil designs, which is very efficient. It slides right in, and you can now pull those out as needed. We have some other various designs or products that we can kind of compile together to make your heating needs even easier. You can utilize pipe insert style, which is using a traditional heating elements, and then kind of creating almost a heat transfer system with a glycol or heat transfer fluid. This is our STFX, where we pre-wire everything in-house, controls and all, and the whole thing mounts as a plate, so you can get the controls, heater, and everything all bolted on. So when you think of service rates and installation costs, you're simply landing your, in this case, 480 power to the control box, and everything else is taken care of for you, including over temperature and process sensors and all that. I mentioned earlier the over-the-side product that we have, over-the-side heaters. We call them OTSs. There's a lot of different versions of these to match different applications. We can get them with fluoropolymer coated elements. Some of them we can get in titanium. We can change the length of the riser, and this is to utilize existing tank. This is to utilize openings in existing tanks, whereas it wasn't planned for heat previously when it was designed. And that's a real big help in the field when you do get into a situation where you've got the install, you've got the product, you've got the facility up and running, and oh wait, we forgot to add heat. So then you're kind of left with two choices. You can either heat it externally, or we can utilize, in the case of this example I was alluding to, we can utilize a manway cover at the top of the tank, and you can affix the heater to the manway cover and still retain containment of your product. You can get, class 1 div 2 designs on these to meet your application and fit into your tank. So it's a really great retrofit when you're putting these together, and they get quite elaborate. I mentioned over here on the right, you can get riser heights to any size you're really looking for, in consideration of obviously shipment and how you're going to get those to site, to just stuff that bolts to the side of the tank, which is really super easy. Something short, like a lube oil type heating down into a sump, or even get creative with the elements design themselves and run the cold section of the heater all the way down to put the heat in the bottom of the tank. Again, real good product to utilize in your designs. Moving on to inline circulation heaters. So an exterior type of tank heating, you're utilizing this in two ways. You can pull the product out of the tank, and this would be more of a sidecar design, where you heat the product and then put it back into the tank, which can add agitation to your tank as well if you don't have an agitator in your tank when you're putting these together. But it also gets the heating system itself outside the tank can be serviceable. So maybe you put some isolation valves, can be added after the fact, can be part of the design when you're putting it together. Maybe serviceability is a consideration, and the LTFX, STFX bayonet style is not an option. You can certainly go with a circulation heater. You can couple this with your own pump and system that's already in place. Maybe make a three-way valve, kind of have a bypass, go through a heater back into your tank, and that's a great way to add heat to a tank that maybe previously already existed and doesn't have the connections for it. Or you can design around it and create a system around that. We have some pre-packaged systems that I'll show you here in a second that include the pump and the controls and all that, but you get the idea from the photos that, product in one side, out the other. These are most utilized for process heating, so like a process system where product's coming in at one temperature, out another, for certain processes in a plant, but you can also utilize it for tank heating. It could be standby to keep the tank itself, like the whole sump or thermal mass warm for the process, or you can use it in line on demand as if you're just pulling off the tank and heat as you go. Mentioned before the heat transfer systems, and we've got many designs for this to heat transfer fluids, water glycol. These include that inline heater most of the time, a pump and controls, but they're packaged together and they can fit to your applications. They can fit to existing applications or future applications, however you want to design them. We also have small package units. We think like zone heating. We can do that as well, or we have an entire line of steam generators, which we have another training later in July scheduled for that if you want to know all about our steam generation available. And all of these products, depending on the range or the thermal input of your process, can also be available not only in low voltage, which we consider up to say 1,000 volts. You can get these in medium voltage of 4160, 6900 designs as well. What would that actually look like in a system loop? This is obviously external heating. You've either got a pump or steam generation pushing it through either coils or the product itself. It can be an either or here. You think of indirect heating. You're going to heat indirectly through a coil, exchanger, maybe a jacket around the vessel. Utilized in pharmaceuticals, more difficult corrosive applications, maybe delicate applications where the heat flux with the product are very important. The whole industry in this, but they're really great for utilizing tanks. Now your tank's going to have to be a little more sophisticated, but that is part of the design as well to be considered. Here's what they basically look like at the factory. Again, talking like a coil system, heat around, think of external. Then you can have a different product, maybe even specialty materials made out of the tank, and you can utilize that with those products. Steam generation. Steam is a great indirect heating medium. So you got steam generation, you run it through a coil. We've got any size available, quite frankly, in your design there. Those can get quite elaborate, but sometimes you have to step back and think about, what am I trying to do? What is the outcome of heating my tank? And honestly, you never want to overlook simple pad heating. Surface heating, we've got pad heaters, strip heaters, enclosure heaters, hopper heaters, and it's utilizing the same products that we're discussing, but now we're putting it on the side of the tank. We're transferring the heat through the tank. Now, this sometimes, depending on the tank material, may not be the most efficient way to do this, but it might be the most it might be the most non-intrusive way of heating a tank, especially an existing tank. And again, depends on your application. Are we doing elevated temperatures or are we doing freeze protection? A good example of a process. This is a dipping tank for for a metal process, but you can even see where they've utilized just our straight strip heaters. Extremely cost-effective way of heating your tank in design. So something to consider. Again, what is my tank? What are the dimensions? What am I thinking? And I'll talk about that in a second. But this is where you have multiple options to heat a tank. It's what's best for the application and what's best for me. You can take it to the other extreme, however. In the case of heat loss, we've had recently a project which utilized a standard strip heater, which again, we're not talking anything elaborate, flanged heaters, circ systems, steam generators, none of that. We used simple strip heaters that were rated for higher temperatures to maintain a tank at 1400 degrees. Pretty simplistic way to do it, but it is a tank heating option that we have out there. And no tank heating option wouldn't be complete without electrical heat tracing, which we have your self-regulating cables, your MI cables. Now, for tank heating, I don't often recommend this to actually heat a product, but for temperature maintenance, to offset losses, this is ideally the product you're going to go with. It's great for, and no matter what, if you are heating a tank or maintaining a tank at an elevated temperature, and when I say an elevated temperature, any temperature above ambient, right? You're going to want to consider heat trace for the incoming and outgoing piping of your product, because as soon as it leaves the tank and that thermal mass and moves on, heat loss starts to get quite more, starts to become exponential the further away from the heat source you are. You can consider insulation, your efficiencies, and that's where heat trace needs to be considered with any of these heating products, from immersion to heat transfer systems. You may want to consider heat trace for that. And we have a full line of heat trace and products available, and I invite you all to watch some of the trainings on those. Getting to the last one of just product examples for now, and then we'll dive into tank heating basics of design. Comfort heating surprisingly comes up more and more, and I see this in water treatment facilities. And it's a little unique, but back to the environment. If you're keeping a tank at an elevated temperature above ambient, well, guess what? It's going to lose temperature. So hence, tank heating could be it will be needed in your process. So strangely, comfort heating, something people don't think of a lot. If the room is kept at the desired temperature of the tank, then you may not need need heat directly applied to the tank. So you think of a polymer tank or a fiberglass tank, or holding, say, corrosive chemicals. This can be a great option that a lot of times gets overlooked. And even I mentioned wastewater treatments, where I see it a lot, and here's one process near and dear to my heart. You'll see this in a lot of my presentations, things that I've kind of worked on. Sump heating. So you think of water treatment facilities, you've got a giant thermal mass of water, but where's my heat loss at when you're talking about below grade installations? Well, the heat loss is at the water surface temperature. The water surface is losing temperature to the environment, the building, the outdoors, and all that. So if you're heating the room and maintaining that temperature, then the losses, it cancels out. So, and that is a very common application. And here's an example of showing that right here, where the auger is for the sump, and there's our two heaters in the top left. We get that a lot. Municipalities use those a lot of times in pump houses, and their storage tanks if they're underground. We also have options for over the side immersion heaters as well. And as mentioned at the very beginning, if any of these heating installations that you utilize, you're going to want to consider temperature control, which can be through a thermocouple and RTD. You're going to want to consider level control for designing a heater to be in a product or submersed. When it becomes unsubmersed, it's going to obviously elevate in temperature quite quickly. Two ways to mitigate that is level control to ensure it never happens, or temperature control. You will attach a sensor to the sheath of the element, and we will know when that happens, and that acts as a secondary device for controlling your heating product to avoid any problems with that. I started with that to give just kind of a quick overview of some of the products to keep in mind that are available to you when you're considering how to heat the tank in your process or your facility or whatever it is you're looking at in your application. Obviously, any of us are available to contact and discuss. Here's kind of a segue into the details. And this is where we say the devil's in the details. A lot of things, you can heat a tank a dozen different ways, but what is optimal for my design? And that's what I'm going to talk about a lot in the second presentation. But for the second half of today, I'm going to give you a quick overview of consideration of all the different things that you need to look at on how you approach your tank heating application and what product or technology is optimal for your situation. Now, this is just a short video of our immersion heater cell in Ogden, Utah, where a lot of these manufactured, but you can even see like considerations of standoffs for the electrical connections. The electrical connections are a consideration. You always got to check how many circuits, how many of those I have. Over the side heaters with hazardous terminal housings, smaller immersion bolt-on heaters, thermostats, control. We're going to talk a little bit about control so you understand your choices and what the implications of your application are. And then from there, just basically specialty designs. It's no different than how do we mate to the tank, what material are we choosing, and then what is the watt density. I'll talk a little bit about that here in a second. I just wanted to kind of give you an overview of that. So where do we get started when we're approaching our tank heating application? I have a tank, I have a process, I have a product, and I want to maintain a temperature. There's a lot of things to consider, but they're all very simple when you kind of step back, and after you read through them, everything seems like common sense after you understand it, right? So what are you heating and why? That's what you start the very first with everything. What are we heating? Now, it might seem simple. Oh, I'm heating water, I'm heating oil, I'm heating whatever product, but you're also heating the tank. You're also heating the ancillary connections, the manway, stuff that isn't insulated. You're heating the pad. Those are all things that you have to consider when you're approaching your heating application. Also, how much heat you need to maintain that temperature or increase temperature of your product. Liquid volume is a big consideration because in these larger tanks, 100-foot diameter tank, that's a lot of volume. But you may want to ask yourself, well, how often is it at 100%? Maybe never, maybe 80%. So those are the things, considerations that you go through. And then obviously the product, the density, the type, the flow, fill rates, major one that gets missed a lot of times because especially if we're talking, if you got a storage tank for any reason, right, you're going to be emptying and filling the tank at some point. How often are you doing that? Is this a case, we get this a lot where I have a tank of X size and design and volume, and they do the calculation for the heat loss, and you get a number, and I'll go through those in details later. Let's say you get 100 kW. There's 100 kW to do the application then. You may not be considering, well, I've got 24 hours before I even use the product. Well, guess what? That means you might need a lot smaller heater than you set out to design or spec out for your application. Tank type's a big issue. Thickness of the tank, the material of the tank. I mentioned before the heat sinks, and we'll dig into those a little bit as we go through here. But it all works out to the same equation. And so we're taking, your thermal input, you think thermodynamics, what do I need to do what I desire? Again, what is my application? What are we trying to do here? Are we trying to heat the tank? Or are we just trying to heat the product in the tank? So then you're going to basically do this consideration for all those aspects all added up. You've got to do the tank, you got to do the support, the connections and other parts of the tank that are taking heat away, the heat sinks per se. And they're all simple. Everything has specific heat. We all know that. Heat diffusion, we're not going to worry about. That's more of process heating where we're either vaporizing or melting a product, heat of vaporization as well. The density all goes into the thermal conductivity, and then we have to consider the losses. Again, no reason to heat the tank if the desired temperature of the product or the tank is not elevated to the environment. So after that, like I said, it's pretty simple questions and considerations from there. What are my tank dimensions? What is the exposure to the environment? And that's all a factor of your fit form of the tank. But also other considerations are: is the tank mobile? A lot of times we'll get people get some immersion heaters, and what on paper looks ideal doesn't entirely match up because the tank's moving, and not that the actual tank moving is going to have any impact on the heat. It can damage the heater. There's a lot of things to consider. So what are we trying to do? The material of construction is a big one, and gets misunderstood a lot of times. You've got thickness of the tank. So to maintain the temperature of a product in a tank, you have to maintain the tank temperature as well. It's also a major part of the heat loss. Is the tank steel? Is it stainless? Bolted tanks are quite common, and you get in the larger designs because, quite frankly, they have to be constructed on site. If you have to put heat in a bolted tank, the tank itself may be carbon steel or something easier to less costly. But without knowing what's in the tank, you always have to ask: is it lined with something? Because there may be a corrosive product in the tank. If it's lined, the tank itself may be steel, but the lining itself allows it to be steel. You go putting our heater in the tank, our heater, gets eaten up or falls apart or corrosion. It was never thought of or considered that the heater, the material compatibility wasn't proper. Get this one a lot: polymer and FRP tanks. Can we put electric heaters in those type of tanks? Absolutely. There's a couple small considerations that we can go into in detail, but basically it's all about support, the made up, and how they fit together. You're basically mounting a steel flange or screw plug to a polymer or plastic tank, which is all fine and good, but here's where we consider the watt densities, the temperature of the element, the length of the cold section of the element. We don't want to obviously heat the nozzle, we want to heat the product in the tank. So all those are considerations and can be designed around if you consider that early on and you know what you're doing. Speaking of immersion tanks, you bolt on, you got your screw plug, your ANSI flange, the connection, it becomes a concern. How long is that nozzle? You see that on the left? That's, sorry, good. You've got, a nozzle length that you have to consider. You obviously don't want a heated section in that. And then you've got the protrusion into the tank. Is the flange you're mating up to a raised face flange? Is it a flat face flange? Is it a ring joint flange? All those things, those designations on a data sheet do mean something, and you need to consider that when you're designing. Is the vessel itself pressure rated? Well, no problem on our side. We can mate up to that flange, and we can offer an ASME designed, certified, and stamped product to mate up to that flange, which will meet the pressure rating of the tank. We just need to know that. And you need to ask yourself that when you're going through your tank design. How do I put this together? And then also, how far are the protrusion in the tank? We can spread the heat over a large area to obviously get more exposure to the molecules of the product you're heating, whether it's water, oil, or solvents or anything. But at that point, then you have to consider support in the tank. Do we have access inside the tank to provide support? In these larger molded tanks, or even polymer tanks, we've had to provide support in those. And in some cases, they'll have to build the support for that, because the heater itself is going to weigh a certain weight, true, but also over time, if these heaters can get quite long, and there's a lot of moment of inertia on that nozzle that can cause the gasket to start to pull away. Could bend and torque on the nozzle, can even cause it to fail over time. And you want to consider that. We have, designing a support is not difficult. The key thing to remember is any immersion length past 36 inches, you want to start to consider support of your immersion heater. We do make some self-supporting designs, but then you're going to want to ensure that your nozzle is built to handle that. And then other things like tank details specific to agitators, level controls. It would be a shame for you to, buy an immersion heater that you think is well designed, but once you go to put it in the tank, it interferes with other, like I said, agitators and things inside the tank that, it renders it unusable at that point, right? So you got to consider that. Where are the retaining walls? How are you installing this? All part of your considerations that we'll go into detail at in the later presentation. I use these as quick examples of things that maybe get missed from the drawing board to the site. And I use the one on the left, and I won't call out the location other than it's in the far north mining application, where everything was designed. The heaters were sized properly to maintain temperature. They also went to fill the tank in the dead of winter at -20, -30 degrees C. And the heaters were not designed to thaw out the product after it was already frozen. So that was something that was not considered or seen on the data sheets when that was done, but those are things that you have to consider. What am I doing? What is the worst case scenario? What if there's a shutdown? On the case of the right, you did everything properly and correct, and you designed and put a right product in place to be serviceable. In the case of the retaining wall that you see there in the bottom left, the heating element is removable, but if you don't understand the heating product or the technology you're using, the removal may not be as advertised. In this case, the customer had to take the whole unit out and actually bend the Schedule 40 pipe, which was quite fascinating, to get it returned, where they could have just taken the element out. So environment becomes a big consideration. Are we at the ocean? Are we in the mountains? If you're at the ocean, corrosion issues with salt is a big consideration on the terminal housing. Are we in a hazardous area? Are there gases present? The tank may be fine. It may be a water tank for all we know, but there may be explosive gases present. The area classification becomes a big issue. Where you mount the controls becomes a concern. And then the thickness of the insulation and type of insulation becomes a consideration in your design. And we'll even talk about thermal gains next time as well, because in some cases you may not need insulation because where this thing is located, we are considering a thermal mass. There's a tank full of product, and there's a way of calculating how long it takes that tank to lose 1 degree in the worst case scenario. And in some cases, when you go to larger tanks, when we design them, it can be a real problem because you're looking at heating requirements of 500, a megawatt, nothing practical for the situation. But in reality, that may not be needed. Worst case scenario design for the area might be -20, but it's -20 for worst case 2 days in a row in the entire year. Well, if you have the proper heating program, like when you're putting thermal heat in there, you can work around that. We can design and prove out smaller designs to give your heating needs as need them. We can do off-peak hours. We can do a lot of creative things with tank heating that you may not consider early on to make your application work a whole lot better. And it mentioned before, obviously the install, the shape of the tank, where it's sitting, the ground pad construction is also a consideration of your thermal needs in your process. So moving on and kind of a precursor to what we're going to talk about next time, what to avoid. So in the case of this, this is just some random examples, but I can tell you that, obviously heavy scaling, that's high watt density, that's poor control. In the case of the element at the top that went supernova, we can talk to the quality of the element that it heated that long, but that got exposed, no level control in your tank. You'll get a thing called pitting, but the burn marks on the right is from poor material compatibility. And then control. You've got to consider control. Maybe it's simple that you need, just on off thermostat, easy control, flip a light switch. But again, back to the very first question you have to ask yourself, what am I trying to do when I'm heating? What is my goal of heating this tank? In the case of the bottom right, the temperature control wasn't even near the heater on the tank, and it melted right through the polymer tank. No fault of the heater, it's clearly heating, right? But control becomes a vital part of any tank heating application. So what are we heating? Is it liquid? Is it gas? Is it both in some cases? Maybe we're worried about the vapor area inside a tank. Is it static? Is it dynamic? That means is the flow coming in, flowing out? Do we need to heat that? These are all things you need to ask yourself. And the answer may be no on a lot of these, which is great, but these are things that you have to consider when you go through your design. The liquid volume, I mentioned that before, a lot of times, tanks aren't 100% full all the time. We don't need to necessarily provide that much heat. You may not have that capacity available. Certainly something to consider in your design and how you put something together. Concentration of the solution. We get into this one a lot. When things don't work out, right? Your concentration can mean the difference of it corroding stainless, it not corroding stainless, it eating through Inconel or Incalloy. So you need to know that. You need to know if it's going to change. Gauge pressure, absolute pressure. I mean, that's, if you got ASME, pressure retaining vessels, we can work around that. I use the example of the flare drum, knockout drum example, because we go from taking the tank dimensions into consideration to heat loss. Well, if we ask ourselves in a case of a knockout drum, what are we trying to do? You're just simply trying to pump off the particulates that knockout drum collects. And we'll go into that in detail. But you don't need to heat, in this case, you don't need to heat the whole tank. You just need the bottom portion or near the nozzle heated that you can pump off the tank when you need to, or that it'll at least drain. So that's something that you've got to consider with what am I doing here? Fill rates I mentioned, and then of course your timing. Do I have 1 hour to do this in? Do I have 2 days to do this in? It's going to affect the type of heater, the size of heater that you provide, and quite frankly, save you money in the long run if it's designed and maintained properly. So Your material compatibility becomes a big issue of how corrosive. I mean, obviously our heaters are metal, they're electric heaters. You got, flange connections, screw plug connections. That's going to be a consideration. The concentration and temperature. Temperature can be a catalyst to corrosion. Our heaters are, again, industrial resistors. Basically, they're a coil winding and magnesium oxide surrounded by a metal sheath. The metal sheath can be, again, one of many metals to match up to your application, but that isn't going to matter as much as the watt density. So if there are mechanicals on the call, you've got your heat flux, as they call it, in exchangers. This is your heat flux in the electrical terms. It's your watt density. And what that is your total output of your heater. So whatever it's rated for, divided by the actual surface area of the heating portion of the heater. That correlates to, basically the size of the heater that we're going to provide. You don't want the heater to be too intense for corrosion issues. You don't want it to be too intense to scorch your product. There are a lot of reasons to consider watt density and what is the proper watt density, your process temperatures, your maintained temperatures of your tank. But there's also the concern of how big the heater becomes. We can, it would be real easy to say, oh, we just make all of our heaters 1 watt density. Well, quite frankly, it varies widely between a good heat transfer medium such as water to a poor heat transfer medium, which would be, air or oil or thick viscous lube oil, something like that. And it can have an impact on the size of heater you're going to install. And there's a responsible way to do that. You'll find a lot of recommendations and charts, as you see on the left, water, steam, 45 watts a square inch. However, some steam generators go up to 100. So that would be half the size. Oil heating all depends on the temperatures you're maintaining. It's all relative to what are we trying to do and what temperature are we trying to maintain? And that's obviously something that we can design and consider as we put into our heating. And then control. Your power switching can be simple on off, thermostat accuracy of plus or minus 10 degrees down to the degree if we're using solid state relay and we're varying the output. And we can get into that in detail a little bit later because I know I'm getting quite long-winded. But again, you've got the 2 basic tank heating designs are either on off, which is your contactor, think of light switch, or your SSR, which utilizes basically the control of a solid state relay to limit the output of the heater. It's proportional. The term turn down ratio comes up a lot, and you can basically dial this down to whatever you need it to be in your output. So hopefully you'll join us the 16th for a detailed discussion into the control and the material selection and obviously the sizing and optimizing the type of heater you choose. But hopefully that was a good overview to get you started on your tank heating applications and what you are looking at doing. And with that, I will now open it up for questions.